Now let's look at patterns of curved arrows for polar reactions. For any reaction mechanism that we are going to study in the next few days, the patterns of curved arrows will be one of these: either nucleophilic attack, loss of a leaving group, proton transfers, or rearrangements. We'll go through them one by one. Nucleophilic attack will contain at least one curved arrow. That curved arrow will begin with a pair of electrons, either a lone pair or a pi bond on the nucleophile, and it'll end on the electrophile. It'll result in the formation of a sigma bond. The end result, the nucleophile is now bound to the electrophile. Here we have a bromide ion, a nucleophile, and a carbocation, an electrophile. Go ahead and draw these two ions on your paper, pause the video, and then draw in the curved arrows for nucleophilic attack, as well as the structure of the product formed. Pause your video now and do it. Did you finish? Did you get this? The curved arrow starts on the bromide lone pair, ends on the carbocation. This results in the formation of T-butyl bromide, as shown on the right. Now we'll look at a case when nucleophilic attack requires more than one curved arrow. The bromide ion here is the nucleophile, and the 2-butanone is the electrophile. The main arrow for nucleophilic attack starts on the bromide lone pair and ends on the partially positive carbonyl carbon. The problem this presents is we would now have 5 bonds to this carbon, exceeding its octet. We relieve this with a second curved arrow. And our resulting structure looks like this. You can think of arrow 1 as representing the nucleophilic attack, and arrow 2 being more of a resonance process. If you just look at 2-butanone, it has the resonance pattern, pi bond with electronegativity difference. So it's got a resonance structure where the pi bond turns into a lone pair on the oxygen ion and leaves a carbocation as well. This also helps you see that the carbonyl carbon is very electrophilic. But the main thing here, arrow number 1, the nucleophilic attack, is the formation of that sigma bond between the carbonyl carbon and the bromide. A pi bond can also act as a nucleophile. Here we have a carbocation and an alkene. The pair of electrons in the pi bond can become a sigma bond, represented like so. And this gives us a new carbocation. The second pattern is loss of a leaving group. You can think of this as the reverse of nucleophilic attack. A pi bond turns into a lone pair. How would loss of a leaving group work here? Well, bromine is the leaving group. There's your curved arrow. You simply turn the sigma bond into a lone pair. What's left over is this carbocation, and the leaving group, which now has 4 lone pairs, and so is a bromide anion. Water is also a good leaving group. Can you draw this molecule on your paper and then the curved arrows that would show loss of a leaving group? Go ahead and draw the molecule, then pause your video and draw the curved arrows and the resulting products. Have you done it? Here's what it looks like. One curved arrow changing a sigma bond into a lone pair. Our resulting carbocation plus our leaving group. Now with 2 lone pairs. Sometimes you'll see loss of a leaving group happening with lots of curved arrows. The key is to recognize the one that's turning the sigma bond into a lone pair. I'll label that as arrow 1 on my diagram. Arrows 2, 3, and 4 are resonance. The third pattern that you've seen already is proton transfer, abbreviated as H plus X-Fer. This always requires at least 2 arrows. One of the arrows looks kind of like nucleophilic attack. That's arrow 1. The difference between this kind of attack and nucleophilic attack is the group being attacked is not an electrophile, it is a proton. And then the second arrow looks like loss of a leaving group. Here, hydronium is acting as an acid, and the acetone is acting as a base. As with nucleophilic attack and loss of a leaving group, proton transfer can sometimes have additional arrows. Here we have hydroxide acting as the base, and the acetone acting as the acid. 3 curved arrows are shown here. You can actually think of this as being like proton transfer plus resonance. To the right, I've shown the 2 arrows you would expect to see with proton transfer. Arrow number 1 looks like nucleophilic attack, although it's not attacking an electrophile, it's attacking a proton. Arrow 2 looks like loss of a leaving group. The result would be this carbanion, but it would be more stable if we use these 2 curved arrows to give you the following resonance structure. Why? Because if you have to have a negative charge, it's better to put it on the more electronegative atom, in this case, the oxygen. Rearrangements happen to produce a more stable carbocation. So you're starting with the carbocation and ending with the carbocation. What makes one carbocation more stable than another? The answer is hyperconjugation. The more carbons bound to the positively charged carbon, the more of these hybrid orbitals are capable of donating electron density into the empty p orbital on the carbocation. Therefore, more substitution gives greater stability. So, the least stable carbocation is the methyl carbocation. It has 0 hybrid orbitals on adjacent atoms to the carbocation to donate electron density into that empty p orbital. Primary has 1, secondary has 2, tertiary has 3. Hence, tertiary is the most stable just by substitution. It should be noted that resonance also stabilizes carbocations. So, an allylic cation is more stable than a tertiary, and a benzylic cation, which has 4 different resonance structures, is more stable than an allylic. There are 2 kinds of rearrangement that will happen to increase the degree of substitution in a carbocation. In the first one, a hydride ion moves from an adjacent carbon to the carbocation. This shifts the positive charge from the carbon on the right to the carbon on the left. This is a hydride ion. It's a hydrogen with 2 electrons. And we know this is hydride shift because the curved arrow starts on the CH sigma bond. Hydrides can only shift by 1 position. Hence, it's called 1,2 hydride shift. But it doesn't have to be a hydride. If you don't have a hydride available, you can do the same thing with a methide ion. That's a CH3 with a lone pair and a negative charge. So down below, we have that methyl group shifting from the carbon on the left to the carbon on the right. That shifts the positive charge from the carbon on the right to the carbon on the left. And we call this a 1,2 methide shift, or just a methyl shift. Can you draw the rearrangement for this carbocation? Go ahead and draw the molecule on your paper. Then determine if it's possible to rearrange it to give you a more stable carbocation. Draw the curved arrows and the result. Pause your video now and do it. Have you got the answer? In order to do this, we need to consider all groups on adjacent carbons. There's 3 hydrogens there, and 3 methyl groups on the carbon on the left. Now, if we were to do a 1,2 hydride shift, that would take us from a secondary carbocation to a primary carbocation. Rearrangements never happen to give a less stable product. However, if we did a 1,2 methide shift, we would now have a tertiary carbocation, which is more stable.